Hey guys, how's everything going? This is JSer, who is not good at algorithms. I'm making this video to prepare my interview. In this video, where I'm going to take a look at 2, 3, 6, lowest common ancestor of a binary tree. We're given a binary tree, we need to find the lowest common ancestor. Okay, say if we're given a tree like this, we need to find the common root of 5 and 1. 5, 1, of course, is 3, right? Yeah, and it's lowest. So how should we do it? Well, for tree, the first one, recursion. Yeah, let's try to find the relationship between the final path, like 5, 3, 3, 5, 3, 1, and the node itself. What's the relationship between them, right? Okay. So for one node and the common ancestor of two nodes, and there are two possibilities, right? The first one, the node is not in the path. Let's say for 6 and 2, the common will be 5, but 3 is not in them, right? If 3 is not in them, then the common ancestor must be in a left tree or in a right tree, right? Yeah, that's for sure. Cool. And now if it is the common ancestor, what will happen? It means in left tree there will be 1, 5, or 1, right? There will be 5 or 1, and in another one will be 1 or 5. So the 5 and 1 will be in separate tree, right? That's the case. Or of course itself would be itself might be the target, right? So for 5 and 3, the common ancestor will be 3. So it means that the target would be in left tree or in right tree or itself. So that's our relationship. So for recursion, how we do it? Well, for case like 5 in left tree and 1 in right tree, we cannot determine the result until the recursion of these two subtrees returns us the result, right? So what we need is that if the tree has 5, if the tree has 1, right? So when we create our recursion method, we are gonna return 3 things. 1, the LCA node, right? Like for 5, we need to return the node. And has Q, P, and has Q, right? If we get these 3, we can get a recursion function. So let's try to do it. When we work on a node, what we'll do? Well, first, if it's null, what will happen? We just return the node is null, right? There's nothing. Has P, false. Has Q, false, right? Now, if node it's not null, we will do what? We will first check the left tree, right? It's LCA left has P left has left has P, left has Q. This will be walk node left, right? If LCA left, if the target common ancestor is found, then what do we do? Well, we just return them, right? We don't need to go to right anymore. Like for 3, we already get 5, then we don't need to go to this tree. It's a waste of time. So just return true, right? When this is true, these two must also be true. Cool. If left is not found, then we try to walk to the right, right? the same. If a common ancestor is found in the right tree, we return it a true. Now what's the case? Now it means there's no common ancestor in left tree or in the right tree, right? So for this node, what will we do? Well, let's say const has p, current node has p, right? Current tree, if it has p or not. It means if left has p, then it must be has p, right? If right has p, then of course it has p, or the root itself is p, right? So its node equals p. It has p. Then has q is the same. Left has q, right has q, or node equals q. Now we know for this node if it has p or q or not. So if both we has p or q, we will return the node. It's the common ancestor node, right? So true. For the other cases, we return null, right? It's not the common ancestor, and we return has p and has q. Well, this is perfect. Recursion is done. Now let's return walk root. I think it should work. Uh-oh, undefined. Okay. I should review one more time before I run the code. Anyway, let's take a look. Walk root, okay, for node, if it's null, we return null false. Is has p? No. If left has p, left has q, walk left. Cool. If found, we return. Yeah. And then we do right. Right has p, right has q, walk to the right. If it is right, okay. And then has p or has q. If we has p means left has p or right has p, or node itself is p. Left has q, right has q, node equals q. If has p and has q, if both p and q are in this tree, then I say this is the, oh shit, I think I need to return the first element, right? Cool. Yay, we're accepted. And let's analyze the time and space complexity. Time, every node actually has been traversed for once, right? So obviously it's linear time. For space, we actually, this walk would be like 3, 5, 6, and then we return to 5, and then 2, oh no, 3, 5, and find 5, and 2, 6, 2, 7, 2, 4, and nothing is found. We got to 3, 3, 1. And the 0, right? The 0 is check. Let's try to log the node. I think it should be 3, 5, 6, 2, 7, 4, 1, 0, 8. All the nodes are traversed, I think. Log node val. Three, 5, 2, 7, 1, 8. Yeah, so yeah, for this one is linear time. Space. Well, for each traverse, actually we use an array to keep the result, but actually the maximum depth of the call stack would be worst linear, right? Worst is linear, like the tree will be a straight line. and we use this array to store the result. But this actually is we return the result as the recursion. So actually, it's linear space. There will be nothing like a. It's not like a 3n, right? We use 3, but it's not, because we first will get the left, and then we do the calculations. So the arrays will be recycled. It's linear time. It's linear space. Well, I think there's another solution for this. This recursion. I think there was another way called much more, not much more, but a little easier to understand. It's that for we are going to search 2 or 2, the common ancestor of 2 and 0. What's the common node? Well, for every node in this tree, there will be a path, right, from the root to it. Like 2, there will be 3, 4, 2. And for 3, 5, 2. For 0, 3, 1, 2. So I think what we need is just to search on the tree, search for a specific node, and get the path. And then we just compare these two paths and find the common ancestor, right? This is another approach. Let's try to do that. Let's first create a function to do the search. Search, well, what we do, it will receive even a node as a parameter, and return what? Return the path to the node. Well, when we are search, we'll of course we'll use recursion. We will go to the root first and then go to 5. So when we make 2, we need to return it. And how we will collect the result, we actually need to pass down the path, right? So actually for search there will be an extra, which is path. Well, so if node is null, we just do the return null, right? The path is null. And then if it is not the null, then what do? We search on the left, right? So const left searched equals what? Equals search node left. With what? With path concat node. Oh, before we search, if itself is the target, we need to return right away. So if node equals, oh, we forgot to pass the target. My bad. If node is target, we'll return path concat target, right? And if itself is not, we search on the left, but we pass a new path with the node in, and then we say if left is found, it's found in the left, and we have the path, right? Then we just return the path. Return this. If it is not found in the left, we search on the right. We will do it to the right. Right search equals search node right. Don't forget a target. Target path concat node. Well, this is the last chance, so we will just return right searched. So this is our search method. So for P and Q, I think, well, path P would be search roots P, right? Empty array as the third parameter. Path Q, search. Now we have two paths, right? Let's first log it. No, we don't need to. So for the path must have the same first element as the root, right? Because every path starts from the root. So we'll say let the result be, and while actually the common ancestor will be the last element, which is the same in both paths, right? So for a while loop, it should end at where? It should end when they are not the same. So path while path P 0 equals path Q 0. When they are the same, we set it to either one of them, and don't forget to shift them out. Path Q shift. And finally, we return the result. Run the code. Seems like working for this case. Let's try to submit. But, oh, we are running out of memory. This is out of memory. Let's try to analyze the time and space. For time, we search, the worst case is all of the node, so for search, and then the second node, well, all of the node, and we will compare it once again. What's the worst case? Well, worst case is all of the node, so it's actually triple N. It's still linear time, right? For space, let's see. We use for each search, we are receiving a path and create a new path. So different from the previous one. When this recursion goes down from root to the leaf node, the space is used, the extra space, the path. There will be still reference to it, so it will not be recycled. It will be not be GC'd, and this extra space will be in the whole lifetime. So the worst case will be all the nodes are searched, and the path. What would be the path? Well, the path would be there will be a path. There will be linear to the depth, right? So for one node, it will be 1 plus 2, right? Plus plus n. So it actually is n squared. This is the space. Plus this is a call stack. Plus linear, right? This is the worst case. Well, this is why you see it says the heap is out of memory. We're actually using a lot of out of memory. Let's try to improve it. Improve the search first. Well, the problem is that we're keeping the path, right? This path actually should be recycled. We're only searching the target. There's no need to keep an extra space for each node, right? We just pass it down. So here, concat, we should not use them. We should use path. While if this node is null, of course we return null, and now we could just push the node in, right? Now the path has the node, so here we just return the path. And for left search, we search on the path. If searched, we return it. If right, we search the path, and here, if right, we found in the right, we return path. No, it should be right searched. Well, it's the same reference to the path. So actually, there will be only one path, right? So when left and right are all down, it means actually there is no element, there's no target with down in this path, right? So we need to go to the sibling, like for 5, all is found, all is traversed. So we need to go to 1. Well, of course, we need to do what? We need to pop the 5 out, right? So this should work. Cool. Let's submit. Well, accepted. You see, for the time and the space, for the time, it's the same. For space, we're not using extra like n squared. You see, we only use one path. So this path will be actually maximum linear, right? So it will be linear plus the cos stack. So it's linear space. Well, you see, since we're using the one path, why don't we just write the path in a global way? Is this better? But this path acting, this is better because search will be a standalone function without any dependence. If you create a global path array, we search, we push, we return true, and if we return. So actually, it's the same. Anyway, let's try to write it. If we write it another way of global path, global 1 array. Okay, so let's say there is a, okay, we use a recursion, okay? No, I'll say create a path empty. So there's no need to path. We don't pass the array. If node is null, of course, return what? Return, but we need to return something. It must be there. Well, we could return null. No, we should not return null. We should just return empty. Return empty, okay. And then we push our node in. If node itself is target, we return the path. But this is global, right? Let's use slice so that when we are calling search P and search Q, no. We should return path. If we okay, let's try to do left search the same. We forgot the path. Just to return true, and here we return false. Return true. Return true. And when we found this, at last nothing is found, so we pop it. Cool. So this actually will stop when the target is found, so we can collect the path, right? So search search root p, const path p equals path, we slice it. Okay, we could use path and reset it. And then search root q. Wow, this is actually a little ugly. Uh-oh, there's some problem. We search right, node right, target. We return false. Okay. Search root p. Search 5. We got 3. We push it. Node is not target. We search left. Target. And it is target, so we return true. And for 3, left is found. We return true. And search right. If right searched, return true. If not, we pop it. So search root p, and we get the path. Reset path, search q. Uh-oh, I see what happened. This while loop doesn't end. So actually, cool. This is another accept approach, but it's kind of ugly, so I'd prefer this one. Pass everything needed to the recursion function as a parameter. This is actually, yeah, cool. So I think this is called backtracking. We found something. If we found, we just return. If not, we'd go to the next one. But we would need to reset the cache data, which is out of memory. Oh, I didn't. Oh, cool. I forgot to leave the previous solution. Anyway, you know what I mean. So this is this one. Okay, this one. I'll copy it. Time linear space linear. So this one is I would recommend it. For this kind of existence check in recursion, we need to stop the recursion as soon as possible. So we return a flag or anything to let the parent know that, okay, I found it. Just stop going to my siblings. For 5, we found it. So you don't need to go to 1. I found it. So for 5, it tells 3 with the flag, right? If we need to find all the solutions, it is not like this. The parent won't listen to the child. We just continue searching the siblings. So this is the technique we're using in the tree search, I think. Hope it helps. So see you next time. Bye bye.